Let's begin the class by doing a revision of yesterday and then we will continue ahead. So today we will learn linear regression in details. Okay. So yesterday what we saw was just introduction of it. Today we will see that in details. Okay. So let's start with a revision. Okay, so what did we see yesterday? We saw the divisions of machine learning. What are the different classes in machine learning? So we saw three classes broadly. One is supervised learning. Supervised learning is that kind of learning which has a dependent variable. Okay. One is unsupervised learning. Okay, where there is no dependent variable. The concept of dependent variable does not exist there. And then we have reinforcement learning. Okay, supervised learning again is divided into two parts. One is classification, one is regression. Classification is when dependent variable is categorical. Regression is when the dependent variable is continuous. Okay, so within regression there are many algorithms. Similarly, within classification there are many algorithms, and the same goes true for unsupervised learning also. So there are no more classes within unsupervised learning. So straight away under unsupervised learning you will have some algorithms. We will see two of them later. But right now in supervised learning we are looking at one of the first algorithms, which is linear regression. We are looking at this now. Next we will jump to another algorithm which will be here. Okay, and then we will see at some algorithms which are common to both. So both can be done using the same algorithms. So after doing linear regression we will do something called logistic regression. Okay, that will be for classification, and then we will see some common algorithms used for both. We'll have some common. Okay, they will be used for both of them. So let's see linear regression in details. So linear regression is a supervised learning algorithm which is used when you have a continuous dependent variable. Okay, so what do we do in linear regression? Linear regression, we use an algorithm known as ordinary least square. Okay, we use an algorithm called ordinary least square. What does it do? It tries to come up with, so the assumption of a linear regression is that the function the function which defines your dependent variable with respect to the independent variables, we assume that that function f is linear. Okay, this is a inherent assumption in linear regression, that that function is linear. So it cannot take any curve or any other shape. It has to be a straight line. Okay, and we will see it can be a line or it can be a plane also. Need not be a line always. It can be a plane also. A plane is also linear. This is a linear structure in two dimension. We will see that today. So what we assume in linear regression is that this function f is linear. Okay, so when you have just one independent variable, if we have just one independent variable, that linear structure will be a straight line. Okay, it will be a straight line if you have only one independent variable. So for example, I can call that independent, so let's say this only I have only x, so then we will assume that f is a straight line. Okay, and what is the equation of a straight line? The equation of a straight line is beta naught plus beta 1 x, where beta naught is your intercept. What is the intercept? Intercept is the point where your line meets the y-axis. This is your beta naught. Okay, this value is beta naught. It can be positive or it can be negative also. If this is your line, your beta naught is negative. Okay, this is your beta naught. In this case, it is negative. And then you have your beta 1 is your slope of this line. Slope of the line can be found by looking at how much are we rising up along the y-axis for every unit increase in x-axis. So that means if you move from, let's say this is 4 and this is 5, so 1 unit increase in x-axis, corresponding to this 1 unit increase in x-axis, what is the increase in y-axis? So this particular thing, this is your delta y. Okay, so y corresponding to zero point 0.5 minus y corresponding to 0.4, so delta y. Okay, this is your slope. So this is our assumption that if you have one independent variable, our line will be a straight line. Now how do we find this straight line? We use the OLS method, OLS algorithm, which states that we try to minimize the sum of squared error. Okay, we try to minimize the sum of squared error. Now why do we minimize the sum of squared error that we saw yesterday? Because if we cannot just take the errors, okay, because they will always be zero. The errors will always be zero because half of the errors will be positive and the other half will be negative, and they will negate each other and they will cancel out to be zero. So we cannot minimize this because this is already zero. Mod also we cannot take. We cannot take the mod because this might lead to multiple lines, multiple different lines as the solution. But we want a single line as the solution. Hence we square the errors. Excuse me. Hence we square the errors and then we try to minimize that quantity. We try to minimize this particular quantity. Okay, so minimize sum of squared errors, sum of squared errors. And what is error? So for one single point, let's say if this is your line and these are your actual points. Okay, let's say these are your actual points A, B, C, D. Okay, and these are the x values, these are the y values corresponding to these points. So in this case, your actual value are the coordinates of the points A, B and C, A, B, C and D. These are your actual values, the coordinates, the x coordinate and the y coordinate. Okay, x1, y1, x2, y2, x3, y3, x4, y4. Okay, so these are the actual values. So we are only concerned with the value of y. Y is our dependent variable. So the y coordinate is the actual value of these points, whatever you get. Okay, now we will use this line to predict. We will use this line to predict. So using this line, we will get some value, some prediction. So usually in some books, you will find you will have an error term also here, because the line always makes some error also, right? The error will never be zero. So for each prediction, you might have some error. If you don't have an error, for example, for point D, we don't have an error, so error will be zero. But this way also it is written. So for point A, your prediction will lie here. Your prediction is giving you the value at this point. So whatever you get from this prediction, using this line, whatever values you get, that will always lie on this line. It cannot be outside the line. It will always lie on this line. Your predictions always lie on the line. Always remember this, because you are using the line to predict. So y is equal to f of x. So whatever x you write, that will give you a y which is on this line. Okay. So the prediction for point A will be this particular point, because this is the y-axis corresponding to the x-axis of A. So x-axis of A is x1, which is this point. So corresponding to x1, this is the point on the line. So that means your prediction is this particular value. So you have some error. You have this as the error. the error is always measured parallel to the y-axis. Okay, not perpendicular. A lot of people make this mistake. They measure the error perpendicular. No, it is not done. It is parallel to the y-axis. Okay, so this is your prediction. Then you take your actual value minus your predicted value. That is your error for point A. So where this is your actual, and this is your predicted. So this particular value. So you are measuring parallel to y-axis, not perpendicular. Okay. So similarly, you find each of the errors like this, and you try to minimize the error. How do we try to minimize the error? So we have two unknowns in our equation. One is beta naught, one is beta 1. So we will take the actual minus predicted whole square. So this is my sum of squared error. Okay. I will try to minimize this quantity, and this quantity I can write actual minus beta naught minus beta 1x whole square summation of. This is my sum of squared error. Now I will try to minimize my sum of squared error by differentiating with respect to beta 1 and with respect to beta 1, and equal to 0 I'll put. So I'll get two different equations from this. If I partially differentiate my sum of squared error, once with respect to beta 1 and once with respect to beta naught, I will get two equations, and I have two unknowns. So I can solve those two equations and get the value of beta naught and get the value of beta 1. That will be my final answer. So there are some values here which I don't remember. In books you will find that. And that you're not supposed to remember that, okay? It's a little big value. So this way we finally get to our equation of the line. So once we have the equation of our line, whatever value of x I give you, so let's say if I give you a x somewhere here, then you will be able to predict an output for me. I give you a x somewhere here, so still you will be able to give me some corresponding y. Okay, so you have trained the machine to give you an output. That is why all this comes under machine learning. So next time your data can be anywhere which was not there before also. So these 4 points you had seen before. Now if even if you get a point somewhere here, let's say this is point E. So for this also you will be able to predict, though it was not in the past data. So you have trained a machine to give you output. So it is known as machine learning. Okay. So this is all that we saw yesterday. Right guys? Anything else did we see yesterday? Any doubts you have? Yes guys, anything else? Are you awake or all of you have slept after your dinner, after your lunch? Okay, Suraj is awake. Okay. Okay, so let's continue ahead now, okay? And we also saw the R codes for these, right? So whatever we did in R, it was pretty simple. So this was all the theory. Yes, Prashant. So we also saw this in R. So in R, it is pretty simple. Let's say df is your data frame, which has all the variables. It has the independent variable and it has the dependent variable also. So how will you run a model? You run a model by using the lm function. Okay, you use the lm function. Lm stands for linear model. Then you write your dependent variable, whatever is your dependent variable, you write its name, you give the tilde symbol, you write the independent variable. Okay. Yeah, Ravi, that's it's difficult, but I get paid for that, right? And also I like teaching. So I come from a family which has many teachers. My parents are teachers. My dad, he was a teacher. He retired recently. My mom is a teacher. My two of my elder sisters are teacher. So I think it runs in my blood. Okay. So linear model, dependent variable, then independent variable, and then you write the name of your data frame by giving data is equal to the data frame. Okay. You do this. So this is your model, whatever name you give here. So let's say ABC. So ABC is a linear model which has this particular dependent variable and this independent variable. So to look at the output of the model, we just write summary ABC, whatever is the name you give here, and you get a whole bunch of output. We saw only a few things yesterday. So from this output, we saw the errors. The errors are also known as residuals. So you will get a descriptive statistics of the errors. So the mean error, the max error, the median of errors, and so on. Okay. And also you get the coefficients. Coefficients are nothing but your beta naught and beta 1. They are coefficients. So beta 1 intercept, and this is the coefficient corresponding to this independent variable. So you get their values. Let's say it is A and B. So that means you finally have your equation. Your equation is dependent variable is equal to B into the independent variable plus A. This is your final equation. Okay. So this is all that we saw yesterday. Yes, Mrityunjay. You will have a data, you will have some data available to you, and you will know what is your dependent variable. That will be in your business problem. That will be in your problem statement. What problem are you trying to solve? Okay. So that will be in your problem statement, and you will be given a bunch of independent variables. Okay. And right now we are what we are doing right now is only one independent variable. Okay. This is known as univariate linear regression. This is a univariate linear regression. Today we will see how we can include multiple independent variables. So your dependent variable may not just depend on one variable, right? It might depend on many other variables. So for example, your sales. Sales of any company depends on the expenditures of the company, in how many geographies the country works on, the number of employees of the company, the market scenario of that company, the economy of the country in which the company is operating. It can depend on hundreds of other factors. So how will we include all of them? We will see that now. That is known as multivariate linear regression. Okay, that is known as multivariate linear regression. What we saw yesterday was univariate. We were including only one variable. Today we will see multivariate. Okay. Okay. So before we move ahead, before we see multivariate linear regression, let me discuss another important concept. Again, this comes from mathematics, which is correlation. Okay. So what is correlation? So remember in your school we used to hear a term directly proportional. Remember in school we used to say this directly proportional and inversely proportional. So for example, we might say, let's say your success is directly proportional to your hard work, right? Your success is directly proportional to your hard work. We all know that. Okay. Similarly, we might say your success is inversely proportional to your hours of sleep that you take. Okay, it might not be true. Okay, this also might not be true. This also might not be true. But I am just giving you an example. Okay. So your success is inversely proportional to the number of hours you sleep. Your success is directly proportional to the hard work that you do. So we have seen this in our school. What does this mean? This means that the more hard you work or the harder you work, the more you will have success. The more successful you will be. Okay? Or the more you sleep, the lesser successful you will be. This is what it means. Okay? So we saw this in school, but we did not we were not able to quantify this. So success can also be directly proportional to, let's say, the family in which you are born, right? If you are born in a politician's family, well, you are very successful. Okay, so success can also be directly proportional to some other factor. So for us, this is also directly proportional, but there is no quantification here. We don't know which, like, is this more or is this less? Which one is more out of these two? We don't know. We just know that they are directly proportional. So correlation is a quantity which will quantify that. Okay, correlation is a quantity which will give a number to that, and the higher the number, the more correlated it is. Okay, so let's see what is that correlation. So first I will write the definition. So it is represented by small r. Okay, and it is called correlation. Correlation, or sometimes correlation coefficient, both means the same. Okay, correlation coefficient or simply correlation. So this, what does this do? This measures the linear relationship. It measures the linear relationship between two continuous variables, continuous or discrete. Okay, it measures the linear relationship between two continuous or discrete variables. Okay, so for example, and the range it can take is from -1 to +1. It can take only that range. It cannot go outside of that. Okay, so -1, and you will have 0 in the middle, right? And this is +1. So if the value is above 0, that means it is directly proportional. If the value is above 0, and if the value is below 0, that means it is inversely proportional. Okay, max you can go is 1. So if you get correlation between two quantities, let's say A and B, as 1, that means they are directly proportional. They are like perfectly proportional. So that means 1 unit increase of A will give 1 unit increase of B. Okay, that is what it means. 1 unit increase of A will give 1 unit increase of B. So that is why the correlation is 1 here. Okay, similarly, if correlation between X and Y is -1, that means 1 unit increase of X will result in 1 unit decrease in Y. That is why it is -1. Okay, so if I have to plot this, if 1 unit increase in X gives 1 unit increase in Y, then you have a correlation of 1. Okay, and for negative correlation you will have a downward slope. That means if you go 1 unit in X, your Y decreases by same 1 unit, so the slope will become negative. Okay guys, so that is defined by your correlation. And what is the formula for correlation? Let's see what is the formula for correlation. Okay, how is it found? So you don't need to know this, because in R you will directly get the correlation, but let's see anyways. How do we get correlation? Okay, so let's say you have your X, some values you have your Y, you have some values for Y. Okay, now what you will do from here is, you will find average X. You will find the mean of all X's. Similarly, you will find the mean of all Y's. Okay, then you will find the standard deviation of X. We all know how to find this now. You will find the standard deviation of Y. Okay, so both these four quantities you will calculate. Then you will calculate this particular quantity, X minus X bar divided by sigma X. you will calculate this number, and similarly y minus y bar divided by sigma y, you will calculate this number. Okay, you will write it down here. So let's say you have some numbers here, you take their average, which is this, you find their standard deviation, which is this. It can be anything, Lalitya. I'm not talking with respect to dependent or independent way. It can be anything. It can be dependent, it can be independent, both can be independent. We are just talking about any two variables, x and y. Okay. So you find this quantity, then what do? You multiply both of these. Okay, let me call this a, let me call this b. So you calculate the quantity a into b. Okay, you calculate the quantity a into b, so you will get again some numbers you will get, and then finally you take the average of a and b. You take the average of a and b. Okay, this number is r, your correlation coefficient. Okay, so I will give you a homework on this, where in Excel you will have to do this to understand the formula. You'll have to do it in Excel. In R it is very simple. You just use a function called COR. COR is the name of the function. You give your x, you give your y. X and y will be both vectors, numerical vectors, and you get the value of correlation. Okay, so let me just show you quickly in R how do you do that. Okay, so I'll randomly generate some numbers. So both quantities has to be vectors. So let's say I'll give some numbers randomly. Okay, not letters, it should be numbers. Okay, so I've given some random numbers here. So this is my x. Ignore the warning. I have a very old version of R which I don't want to update. So I keep getting these errors. And both the elements must have the same length, okay? Both of them must have the same length. Then only you will be able to find these quantities, right? If they are of different length, you will not be able to find. So the moment you multiply these two quantities, if they are of different length, you will get this quantity for one but not for the other. So that will result in a NA and it will not work basically. Okay, so both of them has to be of the same quantity, of the same length. So I run this, I check the length of x, and then I check the length of y to see if they are equal. Yeah, both are equal. Yes, they are of the same length. Both are 12. Okay, so now I will just run the correlation function. I'll give x and y, and I will get the correlation between them. So the correlation between them is minus 0.13. That means they are inversely proportional to each other. Okay, so if they have a NA, you will get an error. So let's say x has a NA now. So one is 13, one is 12. If you find the correlation, you will get an error. Incompatible dimensions. Okay, they are not equal. So you will have to delete your NA and then do that in that case. So the correlation is minus 0.13. That means if I plot this line, how will it look like, guys? If I plot this line, yes, can you make a guess? Yes, if I plot this line, it will have a downward slope, right? So let me plot this line. Plot x comma y. You see, can you identify a downward slope? Yeah, it does have a downward slope, right? It looks like this. There's a line going like this. Okay, you have a point here. So as this increases, the other one is decreasing basically. Not perfectly. If it was perfect decrease like this, you would have gotten a correlation of -1. Okay, that is why you are getting only -0.20 because it is not a perfect downward slope. So this is your correlation. So why is this important? Why are we studying correlation coefficient? Because this helps us identify whether linear regression will work or not. Okay, so if now imagine one of the variables in correlation to be the dependent variable. Okay, one of the variables, let's say, is dependent variable and the other one is independent variable, and you see a correlation between the dependent and independent to be very high, let's say very close to 1. Okay, so what does this mean? Is this good or is this bad? Yes guys, what do you think? Is this good for us or is this bad for us if there is a high correlation between them with respect to linear regression? Yeah, why is it good? Can somebody tell me? Yes, why do you think it is good? Yeah, see, what do we try to do in linear regression? In linear regression, we try to do this, right? We try to come up with this line. So what are we doing here? What we are doing here is nothing but we are trying to explain why. We are trying to find out the value of y if we are given the value of x, right? That is what we are trying to do. If we are given the value of x, we are trying to find y. Now imagine if x and y are correlated. If x and y are correlated, that means they are either directly proportional or they are either inversely proportional, which is good for us, right? Because if they are perfectly directly proportional or perfectly indirectly proportional, that will help us find out our y better because they are perfectly correlated. But if they are not correlated, let's say if it is like this, if this is the if the points are like this, then to find the correlation will be very difficult. The correlation will be almost zero. That means they are not correlated. Okay, they are not correlated, so that means you will not be able to come up with a very good line like this. So let's imagine these are the points. Okay, you have points like this. Now if you find the correlation between these points, if you fit a linear regression line here, it will look something like this. Okay, but and what will be the correlation of the x and y here? The correlation will also be high because you can see a decreasing trend, right? You can clearly see a decreasing trend. That means if x is increasing, your y is decreasing. So that means they are negatively correlated. It is between 0 and -1. Okay, the correlation is between these value. So if that is the case, it will help you capture your y better if that is the case. So it is always a good thing to have correlation between your dependent variable and your independent variable. Okay, if correlation between dependent and independent is high, by high I mean the absolute value, okay, is high, then that is considered to be good for us. It is very good for linear regression. Okay, so this is very important. If correlation between your dependent and independent is high, it is considered to be good for linear regression. because linear regression measures the same exact thing. In fact, if I tell you, okay, we will see that later. R square will come later. Okay. So this is a good thing for us, that your dependent variable and independent variable are highly correlated. If they are highly correlated, coming up with the equation will be easy for us. Okay. So the first task that you have to do whenever you whenever you are basically doing a linear regression, the first task that you have to do is you have to find the correlation between your dependent and independent. Always do this, okay? Whenever you are starting with a linear regression, you have to, first step is to find the correlation and check whether they are highly correlated or not. Okay, and what do I consider as high correlation? So again, that is subjective, but we usually consider R to be high if the absolute value of R is greater than around zero point 0.6. Okay, then we consider R to be high. That means if it is greater than zero point 0.6 or less than minus zero point 0.6. Okay, so that means zero point 0.6 to 1 or minus 1 to minus zero point 0.6. So this is high R, this range. Okay, again this is subjective. Some people say it is 0.5, but somewhere close to this. Okay, so if it is between zero point 0.4 and minus zero point 0.4, this is low correlation. This is low correlation. This is not high. Okay, if it is in this range. This is how, this is the formula used for correlation. Okay. Yesterday we saw the empty cars data set, right? And we also did that analysis on this. Let us find the correlation in that case. So empty cars, this is how the data looks like. Let's find the correlation between our dependent variable, which was miles per gallon, so mpg, and what did we use yesterday? We saw the weight yesterday, right? With respect to weight we were doing, and we will write empty cars dollar weight. Okay, so the correlation is minus 0.86. So is this good or is this bad, guys? The correlation, will it be helpful for our linear regression or not helpful? No, Ravi, this is good, not bad. Okay, it will be helpful for our linear regression. Even though it has a negative correlation, negative doesn't mean it is bad. Okay, it just means that it is inversely proportional. So we never discussed that inversely proportional is bad, right? As long as it is some proportional, either positively or negatively, it is good for us. Proportional means it will help you explain that variable. Okay, so for example, your success is inversely proportional to the number of hours you sleep. So that means you know that number of hours you sleep has a relation with success, so you can take action accordingly. Okay, but if it is not at all related, so for example, success has nothing to do with the car that you have, just an example. Okay, or success has nothing to do with how many places you have visited, so there the correlation will be very small because it has nothing to do with that. So that means you should not use that variable in your linear regression model. Okay, it simply means that you should only include those independent variables in your linear regression model which has a high correlation with your dependent variable. Okay, so let me write this down. Anybody else facing that problem in the video broadcast? Anybody else facing a issue with the video? Okay, so it might be at Nijaguna's end. Okay, so it's advisable, guys, to include only independent variables which have high correlation with dependent variable, okay, in your linear regression model. Okay, it's always good to include independent variables which have high correlation with your dependent variable. Okay, now let us try to see if any other variable has high correlation. So we checked with empty car's weight, right? Let us check with any other variable. So correlation empty cars. I'll check with displacement. Okay, with displacement I will check. Okay, I have to give empty cars, I have to give the dependent also, right? Okay, so it has a high correlation with displacement also. So that means including this also, we should include this as well. So displacement also is an important variable. So this tells us that weight is important to define miles per gallon. Okay, this is what it means. Similarly here also. So here displacement is important to define miles per gallon. Any other continuous variable do we have? So displacement, horsepower also I can include. So what do you think? Horsepower will have positive correlation or negative correlation? What do you think, guys? What will be the correlation, at least the sign between miles per gallon and horsepower? Will it be positive or negative? It will be negative, right? Because more horsepower means more fuel it will burn. Okay. So yeah, it is negative, but slightly less than the previous one. Okay. Okay, so Niranjan is asking, can't we see the correlation between all columns in a single go? No, we can see. But first let us see it one at a time. Then I will show you all together. Okay. So horsepower is also important to define. Okay. So now let us see all together. So to see all together, what I will do, I will write correlation of empty cars, and then using indexing, I will select only those columns between which I want the correlation. Okay, so I want the first column, so I will write 1 here. I want displacement, which is number 3, so I will write 3. Horsepower number 4. D ratio, that is number 5. Weight is number 6. Let's include Q sec also, which is 7. Yeah, that is all. So I'll find the correlation between all of these. So I'll run this. You will get a matrix. Okay, the output will be a matrix which will show the correlation of all variable with all other variable. And by the way, guys, just to ask you a question, I removed that. What do you think will be the correlation of x versus x? Of x versus x? What will be the correlation of a variable with itself? Yeah, you get it, right? Why it will be 1? Okay, this is clear, right? Because if you increase x by 1, obviously the other x will also increase by 1 because they are the same. So correlation, it measures the same quantity, right? If you increase 1 by 1 unit, by what unit will the other increase? That is what correlation measures. Okay. So obviously if you increase this by 1, this also increases by 1. So the correlation will be a perfect one. Okay. So now I have found the correlation between all these variables. I have selected the particular columns using indexing. So you already know what is indexing, and this is what I get. See, so miles per gallon, with miles per gallon it has a correlation of perfect 1. So all these diagonal elements will be 1 because they are the same variable with itself. Okay. Now correlation of displacement with miles per gallon is minus 0.84. Correlation of horsepower with miles per gallon is minus 0.77. Of D ratio with miles per gallon is this. Of weight with miles per gallon is this. And of Qsec with miles per gallon is this. Okay. So whichever you want to read, just take that variable. So weight. So this is the correlation of weight with miles per gallon. This is the correlation of weight with displacement, of weight with horsepower, and so on. So now you know how to read this table, right? This matrix. All of you understand how to read this matrix? What each terms are representing? Just follow the row number, row name, and the column name. So this is the row name, and these are the column names, and you will understand. Okay. So this tells us that we can use displacement, horsepower, diameter ratio, and weight to identify miles per gallon. But including Qsec probably is not a good idea. Okay, because Qsec is not very high. This is low correlation. This has a low correlation, but these other terms are good for us because they all have high correlation. So this is good. This including this in your linear model will not make much sense because the correlation is not high. Okay. That's what I told you, Jagdish. The value that you can select is around zero point 0.6. So if your correlation is less than zero point 0.6 absolute value, you can say it is not a high correlation. Okay. So zero point 0.6 is the threshold that we choose. There is no hard and fast rule. Some people consider zero point 0.5 also. Okay. So around 0.5, 0.55 or zero point 0.6. You can select around that range. Okay. Now let us go to the output of linear regression and study the things that we left yesterday. So we got so many other stuff also, right, as output. Let us study those now. Yeah, mod of zero point 0.6, Lalitya. If it is less than mod of zero point 0.6. Okay. So let's study now. I'll build a linear regression model. Let me call it linreg is equal to lm. I will write miles per gallon. I'll use the tilde symbol and I'll give weight, and I will give data is equal to empty cars. Okay. I run this, then I will see the output summary of linreg. Okay, and this gives me this output. Now let us study the output today in details. So this we talked yesterday. This is just a formula. This is the residuals, the errors. Okay. Now let us see the coefficient. This is the intercept and this is the weight. Okay. Now what is the standard error? So to understand the standard error, we will have to go back to our t-test. We'll have to go back to our t-test. And what did the t-test tell us? T-test told us that if you have a population, okay, if you have a population whose average is, let's say, mu. Okay, then you can take a sample from the population, and let's say the sample average, or you can take several samples from the population. Take a few samples from the population, and if you want to check whether the samples are from this population or not, okay, or if you want to make conclusion about the population by taking these samples. So imagine this to be the entire Karnataka state, and you want to predict who will win this year's election. So you take different samples. So let's say this sample is from Bangalore, this is from some other districts of Karnataka, okay, this is from Mysore and so many other places. You select these samples, and now you want to predict for entire Karnataka who will win. So what will you do? You will take, so these samples will have some average. Each of these samples will have some average. So let's say this is the average x1, x2, x3, and so on. So you calculate the final average now. Take the average of everybody. All these samples take their average, and you call it xi bar. Okay. So this is the sample mean. Okay. All samples mean minus mu. Mu is the population mean. Okay. Divided by sample standard deviation. Now what is this sample standard deviation? Sample standard deviation means standard deviation of all these quantities. These quantities will have some standard deviation, right? So you just find the standard deviation of all these values. Okay, that value is this s, and divided by root n. N is the size of each sample. Now this s is what is written here. This is the standard error. This is that s quantity. Okay, and this is nothing but the average of all those samples. Okay, this is the average of all those samples. This is your xi. This is your xi bar. Okay, this is your sample standard deviation. Okay, this is your sample standard deviation, and t value is nothing but your x bar divided by s. This is your t value. Okay, this is your t value. This is your t value. All clear till now? Okay, so you get your t value here. You get your t value. Now using this t value, you will take this t value to a t distribution. You will take this t value to your t distribution, and you will find the area under the curve. That is, and then you will calculate your p value basically. So p value you all remember. Assuming the null to be true, assuming the null to be true, what is the probability of the alternative or more in its direction? So this will be a two-tailed test. Okay, this will be a two-tailed test, and this is what they are getting. They are getting a very small value. So e means 10 to the power. Okay, e here means 2 into 10 to the power minus 16 is what they are getting, which is almost 0. Okay, which is almost 0. So that means you reject your null hypothesis here. You reject null hypothesis here. Okay, so let us see what is the null hypothesis here. Let us see this in details. Okay, let me explain this. Okay guys, I was on mute. Okay, so let's say you want to do linear regression between miles per gallon and weight. Okay, So miles per gallon and your weight. So you assume that there is a function f which maps your dependent to your independent, and in linear regression you assume that to be this particular line. Okay, so this is in linear regression. This is what you assume. Now you have a null hypothesis here. The null hypothesis that you assume is that weight does not explain miles per gallon. Okay, this is the null hypothesis that you assume, that your weight does not explain miles per gallon. Now when will that be true? What will you do to this equation so that weight will not influence miles per gallon? How can you decide this? Anybody? What will you do to this equation so that weight will not define miles per gallon? How will you put this in this equation so that this becomes true? Yes, guys. When will weight not influence your miles per gallon? Yes, exactly. When beta 1 is 0. No, not when weight is 0. When beta 1 is 0. When beta 1 is 0, whatever weight you give, it will not influence your miles per gallon. Agree, Dibakar? When your beta 1 is 0, whatever weight you give, it will never influence your miles per gallon. So this is your alternative this is your null hypothesis. Okay, that your weight does not explain miles per gallon. Okay, and what will be your alternative hypothesis? Of course it is opposite of this. That means weight does influence miles per gallon. That means beta 1 is not equal to 0. Now we will not say it is greater than 0 or less than 0. We will just say it is not equal to 0, because we are doing a two-tailed test. We are doing a two-tailed t-test. Okay, so this is our alternative hypothesis. So after this, what do? We find our p-value. So what is p-value? What did we learn? What was the definition? Yes, guys, anybody remembers the definitions? Yeah, assuming null to be true, we calculate probability of alternative, right? And here it appears. So this is what was the definition of p-value. So we will assume beta 1 to be 0 and then find our p-value. Okay, so we will do a t-test for that, and that is what is done here. So that t-test is what is done here. Okay, so so here R assumes that whatever data you have, is a sample. Okay, the data that you have is a sample from a bigger population. That is what R assumes, and it does a t-test and finds the value of p. So from here it will go and calculate your p-value, and that p-value is mentioned here. So for weight that p-value is 1.29 into 10 to the power minus 16, which is almost 0. Okay, which is almost 0. So I can write down here that p-value is 0. So what does this mean? P low, null go. So what will I do to my null hypothesis? Yes, I will reject my null. Hypothesis. So that means this is wrong, right, guys? That means this is wrong. So beta 1 is not equal to 0. Okay. So then what is beta 1? If beta 1 is not equal to 0, what is beta 1? So that you will get again from R. That means your beta 1 is what R is giving you, minus 5.34. So that means your beta 1 is minus 5.34. So this is how you interpret the output of a linear regression. So now you got your value of beta. So you can come with your equation. So beta 1 is minus 5.34 into weight. Okay. This is how you interpret the output. And this is very important, guys. To interpret the output, it is very important. So what you see here is a t-test going on. And from the t-test, you get the probability out, the p-value out. This is your p-value. Okay. And let's say you do not. Yes, if your p-value was high, if your p was high, your null will fly. That means you will not be able to reject your null hypothesis. That means your beta will not be important. So let me do one thing. Let me include the other variable. What was the other variable we had, which was not important? It was, I think, this qsec, right? So qsec had very less correlation. So let me try to include qsec instead of weight. No, but this is also giving you a very small p-value. It is giving you 0.01, so 1%. So you will still not be able to reject your null hypothesis. Okay. But if you include something weird, it might give you a high p-value. In that case, you will not be able to reject your null hypothesis. So beta will become 0. That means you should not consider that variable. That variable is not important. Are you guys following? Okay. So p-value basically helps you decide whether that variable should be included in your model or not. Okay. That variable should be included in your model or not. So only if your p-value is less than 5%, you should include it in your model. Otherwise, you should go for a different variable. Okay. Let's say you don't remember. So a lot of people in the industry, they don't know what is p-value and all. They just look at this star. You see these stars here? So this star corresponds to your p-value. If your p-value is between 0 and 0.001, you get 3 stars. If your p-value is between 0.001 and 0.01, you get 2 stars. Okay. And if it is between 0.01 and 0.05, you get 1 star. And after 0.5, you just get a dot and then nothing. So if you have at least 1 star, you can select your independent variable only if you have at least 1 star here. At least 1 star you should have. So even if you don't understand p values and all the stats behind it, you can still run linear regression flawlessly. Okay. You just concentrate on these stars. So R is trying to tell you that this is very important. 3 stars you are getting, so very important. So at least 1 star you should have. To say that the variable is important, at least 1 star is needed. Okay. So after this, what do we have? After this, you have residual standard error. Again, you can ignore this on 30 degrees of freedom. So degrees of freedom again is decided based on degrees of freedom is, so what is degrees of freedom? So for people from mechanical background, they would have read about degrees of freedom. So it is a very difficult concept to explain. Let me give you an intuition. Okay, I'll just try to give you an intuition of what degrees of freedom is. Let's say if I tell you that the sum of three numbers is 5. Okay, I'm telling you that the sum of three numbers is 5. Okay, so now I'll be deciding what is the degrees of freedom of this equation. How many degrees of freedom does this have? This means that how much free I am to take numbers here. How free I am to take numbers here. Okay, so here I can give any number, right guys? I can start with any number I want. Let's say 50. Any number I want I can give here, right? So this is your one. Here also I can give any number I want. Whatever number I want I can give here. Okay, let's say I give 100. Okay, Now can I give here, can I give any number that I want? Can I give any number that I want here? No, right? Because the sum has to be 5. So I'll have to give minus 145 here. I don't have freedom here to give any number I want. So degrees of freedom for this equation is 2. Because at two places I was free to give whatever number I want. But at the third place I had to choose the number according to the equation. So this equation has 2 degrees of freedom. Okay? So this is an intuition to understand degrees of freedom. So on similar lines, in a linear regression or in a data frame, your degrees of freedom is number of degrees of freedom is number of rows, okay, plus number of columns minus 2. This is your degrees of freedom. So in this case, our how many rows do we have? Oops, you're getting 41. You have 32 and n call is okay. I am not sure why that formula is not holding true here, but as far as I know that is how it is calculated, but it is showing 30 degrees of freedom. Okay, anyways, this is not a very important concept. Okay, so you can ignore this, but this is how it is calculated. Okay, this is the intuition to understand degrees of freedom, that how freely can you move. Okay, maybe this formula I'm not very sure. It works in most cases, but right now it is not working. I'm not sure why, but I'll come back to this formula again. Okay. Okay, so that's what it is telling you, residual standard error. You can ignore this line. Now multiple r square. What is multiple r square? Let's see this. This is very important. Okay, multiple r square and adjusted r square. This is very important. So so this is about building the model. Okay, this is about building the model. We have seen everything. We have seen what is the hypothesis test that goes inside a linear regression model, and we saw how do we identify whether the independent variable is really helping our model or not. Okay, if the p value is very small, if it has at least one star, that means if the p value is less than 5%, then the variable is helping our model. Okay, the independent variable is helping our dependent variable, otherwise it is not. Okay, we have understood that. Now let us see how accurate is the model. Okay, you can come up with many models which has 3 stars or which has important variables, but how do you decide which is the best model? So that means we will come to evaluation parameter, evaluation or model accuracy. We will check the accuracy of the model. So how do we check that? Let's see. So to check the accuracy of a model, we have a parameter called r square. Okay, capital R square, which is also known as coefficient of determination. Okay, capital R square is also known as coefficient of determination. As the name suggests, it is square of a quantity, so it can take values, only positive values, and between 0 and 1. It can only take values between 0 and 1. Okay, and the best value is 1. Worst value is 0. Okay, 1 means they are, so this is a very similar concept to linear to correlation. Okay, whatever we saw small r, this is a very similar concept to small r. Okay, so this also measures r square, also measures the linear relationship. This also measures the linear relationship between actual and predicted values. Okay, so this R square measures the linear relationship between actual and predicted values. Okay, in fact, the formula to calculate R square, this capital R square is nothing but small r whole square. Okay, but this small r should be the correlation between your dependent, okay, dependent and predicted dependent variable. Okay, what is this predicted dependent? Predicted dependent is what you predict using a linear regression. Are you following, guys? Too many stuff coming your way, but are you following? Yes, guys, are you following? No, this is capital R. Okay, not difficult, Lalitya. You will find it easy. Okay, you'll find it easy only because you are looking at this for the first time. You are finding it slightly difficult. Okay, but it is easy. So let me take a fresh page and explain again. Linear regression is the easiest algorithm in machine learning, by the way. The other algorithms are much tougher. But this involves a lot of statistics. The other algorithms, they don't involve a lot of statistics. This involves a lot of statistics. Okay. So stats, you will not see much of stats in the other models. So most of the stats is in, because these models have their origin in statistics. Other models have their origin in computer science, but the origin of this model is statistics. Okay. So let me explain again the correlation that we saw. Okay, the correlation small r that we saw, that is a general term. Okay, that is a general term between any variable, any two variable. Okay, so this is a general measure between any two variable, not just between dependent and independent. Okay, this is a general term between any two variables. What does this tell you? This tells you whether two variables are related to each other or not. That is what it tells you, nothing else. Okay, it just tells you that these two variables are related to each other or not. Okay, and it is always between two variables. You cannot find this between three variables. Okay, at a time you can only have two variables. That is why in R's output you will see the correlation of two variables at a time. So miles per gallon with miles per gallon, miles per gallon with displacement, and so on. Okay, you cannot have between two or three or more variables. It has to be between two variables. So this is your correlation small r. Now when we build a linear regression model, now coming to linear regression model. Now in linear regression, what do we see? In linear regression, we try to find our dependent variable using our independent variable. Okay, this is what we try to do. Using independent variable, we try to find our dependent variable. So if you see it just in this way, they are very similar, right? Only that I have replaced any two variable with my dependent and independent variable. But they are in fact measuring the same thing. Okay, they are in fact measuring the same thing. So correlation, you can say it measures, it just quantifies. If I have to put it in another way, it quantifies if it is positively or negatively proportional. Okay, it can go between -1 to +1. Okay, so correlation just quantifies what we studied in school, that whether it is positively or negatively proportional. Okay, it will just quantify that, give a number to that. Okay, but linear regression, what it does, it finds the same quantity Okay, but between two specific variables, between dependent variable and independent variable, it has to be these two specific quantities. You cannot find r square. So we are talking about r square here, coefficient of determination. Okay, so this is r square, capital R square is used only for these two specific quantities, not for any random variable. Okay, only when you are doing a linear regression. So this comes into picture only in linear regression, but this is used in general. This is used in general. Okay, but this is used only with respect to linear regression. So this tells you that what is how good are they related to each other. Okay, it can be positively related, it can be negatively related. So small r will tell you whether it is positive or negative. Okay, whether it is increasing or decreasing, it will tell you that. But r square will just tell you whether it is related or not, whether it is related or not. So it has to be between 0 and 1. If it is close to 1, best value is 1, that means it is related. That means it is related. Okay, now is it, how is it related? Is it related positively or negatively? That the sign of beta 1 will tell you. That you don't have to be worried about. That the sign of beta 1 will tell you. But how well is it related? That you know from r square. If the r square value is close to 1, that means it is highly related. If it is close to 0, that means it is not well related. Okay, so the r square measures that particular parameter. And r square is nothing but it is r whole square between your dependent and your predicted dependent variable. Okay, capital R square is this particular value between your dependent and predicted dependent whole square. Now is it clear, guys? Little bit clear? Take a moment and just try to understand this. I'll pause for a moment here. Or do you want a break? We have, it's 3:30 now, 1.5 hours. Do you want a break? And maybe during the break you can try to digest this. Okay, so let's take a 10 minutes break. After the break I will repeat what I have just covered now. Okay, so fresh your mind, and then we will discuss this again. So let's meet at 3:40. Okay guys, 3:40. Okay, I'll see you then at 3:40. The threshold, there is nothing as threshold in r square. Okay, the better, the higher the better. It depends on the data actually. If your data is very dirty, to get a r square of 0.5 also will be difficult. Yeah, the higher the better. So the best value is 1, but it might be very difficult to get a complete 1. So the higher the better. So around 80% is considered very good. But if your data is very tough, if your data is dirty, even to get 60% will be very difficult. So it all depends on your data. Okay. So we will discuss this in details, and we'll have lots of examples. Okay. Okay. Take a break, Laritya. Okay. So let's resume. So what we were discussing is first one concept, which was the concept of small r, which is known as correlation coefficient. Okay, so correlation coefficient is just a parameter which tells you how related are two variables. Okay, this just tells you how related are two variables. Those two variables can be anything. Okay, it can be anything. it tells you how related are those two variables. Both of them, of course, they have to be continuous. You cannot have categorical and another continuous, or both categorical. It has to be both continuous. Okay, so this quantity, we saw how this is measured. This is how it is measured. Okay, this entire thing divided by n, where n is the number of points you have, okay, of both x and y. So this is your correlation coefficient, small r. Now there's another quantity which is very similar to this, but which is used in case of linear regression. Okay, so this has nothing to do with linear regression, guys. This is just statistics. Okay, this has nothing to do with linear regression. We haven't started a linear regression here. These two variables can be anything. It can be any variables. Okay, now we will see another parameter which is used to evaluate the accuracy of a linear regression model. Now we will see r square. What is r square? It is known as coefficient of determination. What is its usage? It is used to evaluate the accuracy of a linear model. Okay, so r square is known as coefficient of determination. It is a quantity that is used to evaluate the accuracy. How good is your linear model? It is used to find that out. Okay, and thus that just happens to be related to this r, because this r can be found by taking the actual values and the predicted values finding the correlation coefficient between them and just squaring them. This is how this r square can be found. This is the formula for r square. Okay, now is it clear, guys? Let me just show you this, that this is equal to that. So this you can get in your r output itself. See, this is where I'm getting. This is your r squared value. Okay, 0.7528. Okay, so that means if I find the correlation between my actual and my dependent, what should I get? So if I find the correlation between my actual values, so my actual values are present in motor cars dollar miles per gallon. This is my actual value, and my predicted values, you will see, are present in here. Okay, so you see I'm getting the correlation as this, the correlation between my actual values. No, it is COR, it is not R. There is no function as R. Okay, it is COR. Okay, so correlation between this is my actual value and this is my predicted values. I'll tell you how I got this predicted values, but as of now just assume that this is the predicted value. I got this as the correlation. That means if I take the square of this, I should get the R square. Okay, so let me take the square of this entire thing. I will take the square of this entire thing, and I am getting 0.7528, which is what is coming here. So R square is equal to the correlation between actual and predicted whole square. Okay, that's what I have written here. R square is equal to the correlation between actual and predicted whole square. Okay, guys. So that is what this is telling you. Okay, what is adjusted R square, we will see now. We will see this later. First assume this is your R square. R square is also known as multiple R square. Okay, so this is your multiple R square. And what is this F statistics? We will come to this later. Okay, so we will come to the other terms later, but as of now let's take things in installments. Understand this you have understood. This is just the formula that we have used. This is the summary statistics of the residuals or the errors. You have understood this. Coefficients, this entire portion you have understood. Okay, this is the coefficient values. This is like the standard deviation or standard error. This is your t value coming from a t test, and this is your p value from a hypothesis test. Okay, if p value is low, you will reject the null hypothesis, and the null hypothesis is that weight is not important. So you reject that decision and you say that weight is important. That means your beta is non-zero. So it is 5.34. So you have understood this. Then you understood what is this. No, not this. You understood what is this r square. Okay. So a few things remains which we will see later. So let's take things in piece by piece way. Okay. All clear till now, guys? Okay, now let us see a few additional parameters that we can get from a linear regression's output. So this is your linear regression's output, right? My linear regression model is linreg. So I'll just copy this name and I'll paste here, and the moment I write dollar after it, you see I get some options. I get these options after dollar. So let's see what are these options. Okay, so the first option is coefficients. So what does this mean? Coefficients, we all know coefficients means beta and beta naught. So let me run this. See, I'm getting my intercept and I'm getting my coefficient corresponding to weight. So instead of getting this entire output together, you can just calculate, see the coefficients also. Instead of running the summary command, you can just run this and get the coefficients. So this will also directly tell you what the equation is. So the equation is miles per gallon is equal to 37.28 minus 5.34 into weight. Okay, so that is what this coefficient gives you to get beta naught and beta 1. Okay, now what is the other option? I will write linreg dollar. The other option is residuals. So what do you think this is, guys? Yes, guys, what do you think this is? This is the error. So how many errors you will get here? How many values of error will you get? 1. No, if you add you will get 1. If you add all of that you will get one error which will be 0, right? But these are individual errors for all the rows, for all the points. So how many errors should be there? So let me show you the data set. Our data set looks like this. Okay, so this is how our data set looks like, and each of these are 1 point. This is a point for us. Okay, this is 1 point, this is the other point. These are all observations. Yesterday we saw, right? Observations are records. So for each row you will predict some value of miles per gallon. So the actual value is 21 and you will predict some value. So actual minus predicted will give you the error. So yeah, Devmita is right. You will get as many errors as the number of rows. Yes, exactly. As the number of rows. So how many rows do we have? If we write n row empty cars, I have 32 rows. That means I should have 32 errors. So if I take the length of this, it should be 32. Some of the errors may be 0. Most of them will not be 0. Some may be 0 also. So see, the length is 32. So this is error corresponding to each point. Okay, if I run this, I will get these errors, and each error, see, each row has a name to it, right? So Mazda RX4. So what is the error in prediction of Mazda RX4? It is this first quantity. Mazda RX4, this is just the half name. The full name is not given here. It's not shown. So this is the full name of that car. So the error corresponding to Mazda is minus 2.28. Okay, minus 2.28. That means actual value was 21.0. What we predicted was 2.28 less than that value. Okay, or 2.28 more than that value. That is what we predicted. So similarly for all the cars we have your errors here for all the cars. Okay, so last one is Volvo 142e. So Volvo 142e. So actual value was 21.4. What you predicted was 1.02 miles per gallon above that. Is that clear, guys? So this is to see the errors. Okay. Now let's see the third one. Third one is lin reg. I will see so the third one is not required. You can directly go to fitted values. Okay. We can directly go to the fitted values. Not all are important here. Coefficient is important. Residual is important. We can directly go to fitted values now. Okay. So these three are only important here. We'll directly go to fitted values, and if I run this, what do you think I will get here, guys? Yes, exactly. This is the predicted value as per the model. Okay. These are the predicted values. So you see, I'm getting one predicted value for each of the model. So these are the predicted value. Okay. So for Mazda, I have predicted 23. But what actually was for Mazda, the actual value was 21. But I have predicted 23 point something. So your error should be this particular quantity. See. So now it is making sense. So fitted values is the predictions. Okay. So these are the three important quantities that you have. That is why when I was showing you the R square value, I was showing you this. I took this fitted values there because this is my predicted value. Okay. So can I find my R square now? Can you tell me a formula to find R square? Can somebody write it down in the chat box? Can you write the formula for R square? So one formula is directly taking from summary. So one formula is directly taking from here. So this is the R square. But can we calculate it manually using these three things? Can somebody write it down? Based on what we just learned here, this formula. Can you write it down? I'm waiting for an answer. Okay, so Lalita has given the entire explanation. Okay, this is for small r. Yes, Lalita, you are right. Okay, this is for small r. I'm asking you the formula for capital R square. This capital R square. Okay, square of this. So yes, so Jagdish is right. So you could have easily given me this, right? So correlation between the actual values. My actual values are in my data frame. Okay, my actual values are in my data frame, miles per gallon, and my predicted value is here. This is my predicted value. Okay, so I can just square this. So Lalita, you could have just given me this formula instead of giving the entire explanation of it. Okay, so this is what I was looking for. Now if I run R square, I will get the same value that I have got here. I showed it to you some time ago. Okay, so 7528, I am also getting 7528. So this is the formula for r square. Is it clear, guys? Is this clear to everybody? Okay, so r square is the coefficient of determination. R square best value is 1, higher the better. Okay. Yes, exactly, Divakar. Predicted values will always lie on the line. So if I have to show you the line, yesterday I showed you, right? You can use the plot function and draw the weight. So your x variable is your weight, your y variable. Okay, you can run this and then you can write, oops, where is the line? Okay, the line is not coming here. Yesterday I used some formula, right? I forgot the formula. What was it? Sorry guys, I had somebody at my door. Okay. Yeah. So I was trying to draw the line using the command. Yesterday I drew that line. I forgot the code for it. So was it? It was ab line linear model. I think this will come first. Yeah, this is the line. Okay. So this is the line you are trying to draw, and you can see, guys. See the error corresponding to this point is less. So in this point, your error is only this much. But for some points the error is high. So for this point the error is this much. Okay. And for this point the error is this much. The error is always parallel to your y-axis. Okay, for this point the error is, so the line will go something like this. For this point this is the error, for this point error is big. Okay, so these are your error, the values of error. So if you add all the errors, some are positive, some are negative, you will get 0. Okay, so for r square, higher the better. Okay, so is it clear till now, guys, everything? Okay, now let us come up with different models. Right now we have just seen one model, right? We saw one model which had weight as its independent variable. Okay, now let us come up with another model with a different independent variable. So let me call it reg2. So it will also be lm, miles per gallon, tilde symbol. Let me use the horsepower now. Okay, so looking at the correlation, let me show you the value of correlation. So looking at the correlation, what do you think? Which independent variable will give me the highest value of r square? Looking at the correlation, tell me guys. Looking at this correlation, this chart, this matrix, which independent variable do you think will give me the highest value of r square? Because r square is my accuracy, right? The higher r square means the better it is. So which variable will give me highest r square out of all of these? Okay, Dibakar says displacement. What about you guys? What about the others? 1 and 2. What is 1 and 2? What is 1 and what is 2? So out of these variables, which one will give me the highest value of capital R square? First and second column. So you mean this one and this one? So this we will not include because this is our dependent variable. You cannot have the dependent itself as the independent. Okay. You cannot have the same variable, right? So that means you are saying displacement. No, the best. I am asking the best. So only one you have to select. Okay, yeah, that is correct. So guys, it is weight. It is having higher correlation. See, it is 0.86, but this one is just 0.84. And r square is nothing but square of this quantity. So square of this will give a higher number, right? Because this is bigger than the square of this. Okay, so this is the best variable to be included, and this will not give a good model at all. So let's try with qsec. So if I take qsec and if I do a summary of linreg2, you see I will not get I got a r square of only 0.17. Only 0.17. Previously, if you see, we were getting r square of 0.75, which was very close to 1. But this is closer to 0 than to 1. So this is not a good model. Okay. So I will say this is not a good model. Okay. So now you know how to create two models. You have learned how to create a linear regression model, and then you have learned how to find out which model is the best. Okay, if you have, so you can create many different models like this, right? Similarly, you can create another model with horsepower, you can create another model with d ratio, and so on. Now you know which one is the best. You just look at the value of r square and you find out which model is your best, basically. Okay, okay, so we were discussing model evaluation parameters. Okay, so we were discussing how do we evaluate a model, and one of the parameters we saw is r square. Okay, using r square we evaluate a model. The higher the r square, the better the model is. Okay, so this alone is not just what tells you that this is a good model. Okay, there are some additional parameters also. So let us look at the second parameter. So the second parameter which helps us identify the r square is the error parameter, which is sum of squared error. Okay, which we saw, this is the quantity which the algorithm tries to minimize, right guys? So this also can be measured to identify a good model. So what do you think, higher value of ssc will be good or lower value of ssc will be good for the model? Lower value, right? Because it is a error term. R square is a accuracy term, so higher the better, but ssc is a error term, so lower the value the better it is. Okay, so let's find the sum of squared error now for the two models that we calculated. So we calculated the accuracy, we calculated this model, right? Let me call it linear regression 1 instead of linear regression. Okay, so this is my linear regression one. Now how do I find the sum of squared error here? There is no direct function which will give you. So any idea from using these terms, can you suggest me a way how I can find the sum of squared error? The answer lies in the highlighted portion. I have to find the sum of squared errors. Okay, that means I have to take the error for the first car and I have to square it, then find the error for the second car and then again square it. Similarly, square the errors of everything and then add it. Okay. Yeah, so Mitunjay is partially right. You just square the residuals. Residuals is the error, you square it. But squaring it will just square it. I want the sum of squares, so I have to add it also. Okay, Mitunjay. First you will square it and then you will add everything. Then only you will get the sum of squared error. So to find SSE, what you can do, you can take linreg1 dollar residuals and you square it and then take the sum of everything. Okay, I take the sum of everything. If I run this, this is the value of sum of squared error for the first model. Okay, so this is the value of sum of squared error for the first model. Similarly, I can calculate the sum of squared error for the second model. I'll just copy paste this and change linear regression 1 to linear regression 2. Okay, this is my sum of squared error for the second model and you can see it is higher, right? Because I did not use a good variable. I used qsec here. Even the r square was bad for that, so the error is also high. Okay, so using any r square or sum of squared error, I can determine which model is better. So even r square is telling me that the first model is better. Even linreg1, the sum of squared error, is also telling me that the first model is better. Clear, guys? Do we need to run line 31 and 32 before 33? Yes, of course, Dibakar. Otherwise, how will the model know what is this? How will R know what is linear regression 2? It will not know, right? Without running this, you will not be able to do. You must first create an object. Yeah, if you have run, then not required. So it is required only once. Once after you open R. After that, you can use at any point of time you want. You don't have to run it again. Okay. So this comes from day one lecture. So when the moment you run it once, it will be created here. You see these variables, right? It will be created here. And once it is there, you can use it. Once it is there, you can use it. You don't have to run it again and again. Okay. Okay. So SSC, you are comfortable with SSC now? No, can somebody tell me what will be the unit of SSC? What is the unit of SSC in this example? In this example, yeah, it is square of the units, right? So miles per gallon whole square, right? So it might be maybe kilometers per liter. So in this case, it is miles. So miles per gallon basically. So miles per gallon whole square. This is the unit. Now, do you think this unit is very interpretable? Because you have this square, right? So we know how do we measure kilometers per liter. But if somebody tells you that my car goes 100 kilometers per liter whole square, do you think it is interpretable? It is slightly difficult to understand, right? Why is he telling me 100 kilometers per liter whole square? He could have directly told me 10 kilometers per liter. This will be a better term, right, to understand than this. This is rather confusing. Square of the units. Okay. So the sum of squared error is not interpretable. That is a disadvantage. Sum of squared error is not at all interpretable. Okay. So what do we do then? So we will have to somehow make the units as gallons, miles per gallon, instead of miles per gallon whole square. So how can we make the units interpretable? So because for that we have another error parameter which is known as RMSE. Okay, root mean squared error. This is another error parameter. Why we use this? Because SSE is not interpretable. Okay, so we use another error parameter. So have you heard this word somewhere? Have you heard this word somewhere? Where? Standard deviation, right? Yes, this is exactly the same parameter. This is the same parameter, but in standard deviation you have root mean square of deviations from average. Okay, here you will have root mean square of error. So that means you will take all the errors. Okay, so how do you find the errors? You take the actual value minus the predicted value. This is your error. Okay, then what do you do? This is your, you got your, so here also you will go from left to right, sorry, right to left. Here also you will go from right to left. You take the error, this is your error, you square it, you square it, then you take the mean of it, I take the mean of it, and then you take the square root. So take the summation and then take the square root. This is your RMSE. Same formula as standard deviation, but in standard deviation this is average, right? Here this is your predicted value. This is the error in between. In standard deviation, if you remember, it is xi minus x bar. So this is the formula for standard deviation. Okay, this is very similar to that, except that you have the error here. Here we have the deviation. So this is our deviation. Okay, here we have the error instead of deviation. So error is also one kind of deviation, right? Error is also like a deviation from actual value. So that is why this is the formula. Now if you take the units of this, the units will be same as miles per gallon. So it is very interpretable. So the advantage of RMSE is that it is interpretable. Okay, clear guys? Okay, now let me give you another example. Let's say I tell you that my RMSE for a model is 10. Okay, I tell you that my RMSE for a model is 10. Okay, before going into that, let's first find the value of RMSE for both these models. So I will find the value of RMSE for both these models. Let me find. So RMSE. So can somebody tell me the formula? What should I write? Yes, think and tell me the formula if you can. What will be the value of RMSE? No, Abhishek, how can it be that? Standard deviation of residuals. No, I just gave you the formula, right? This is the formula. All you have to do is implement that formula in R now. Yeah, so Dibakar is right. Root mean square of empty cars and fitted values. That is what is the formula, but you have to write that down in a mathematical formation. Okay? It is not the standard deviation of residuals, Abhishek. Okay? It is root mean square of the deviations of predicted values from the actual value. So this is how we can find that. First I will calculate the error. So the error I can calculate using this. So this is my errors, right? These are my errors.
or it is not required to do that. I can directly find the errors. You can directly find the errors from this also. Dollar residuals. This will directly give you the errors instead of, so both you can use. You can either calculate the error yourself, or you can use this particular term. This gives you the error. So I'll just copy this. So I have the errors. Then I have to square the errors. I have to square the error. Okay, RMSE. Error is done, square is done. Now I have to take the mean of it. So to take the mean of it, I'll divide it by the number of rows. Okay, I'll divide it by the number of rows, and then finally I have to take the square root of, okay, after this I'll have to take a sum of it. I have to take a sum of it, and then finally I take the square root of everything. Okay, root means square error. So at last I take the square root. So this is my RMSE. Okay, so this is my RMSE value. It is 2.94. Okay guys, is this clear? Is this formula clear? I have just implemented what I wrote here. So this is in maths. I have written this in R now. First I have taken the error. I have squared it. Then I have divided it by the number of rows that I have. Okay, the n value here, this n, and then I have taken the square root of everything. Clear guys? Okay, so my root mean squared error is 2.94, and it has the same unit as miles per gallon, so it is interpretable. So similarly I can find RMSE for the second model also. So RMSE for second model, I'll just replace linreg1 with linreg2, and I will run it. So you see I'm getting 5.38. Okay, so RMSE is also error term, so this also should be the lesser the better. Okay, just like sum of squared error, this is also error term, and you can see the first model is giving me again a better output. It is giving me 2.94, whereas the second model with QSAC variable is giving me 5.38. Okay, so this is also telling me that the first model is bad, is good, sorry, the first model is the better one. Yes, Niranjan, you can use that as well. That is correct. It will give you the same output. So I can show you here. Instead of writing 0.5 here, you can just use the SQRT. That will give you the same answer. Okay, both will work. So there are many ways of doing these things. Okay. Yes, guys, any doubts? Okay. So whenever there is an error in any line, R will show you the error. Okay. See, it is trying to show me here that I have missing argument to function call. See, because I have given a comma here and I have not given anything after that. So this line I have a error. So R is trying to tell me. So you can identify the error like that also. Okay. Now it is that error is gone now. So even without running, you can know if there is a syntax error. You can know even without running it. Okay, now let's come back here. Now we discussed what is R square. It is the accuracy parameter, higher the better. We saw what is sum of squared error. It is the error parameter, lower the better. Now SSE has a disadvantage that the units are not interpretable. So it is very difficult if you tell somebody that my sum of squared error is some particular number. If you give, it will be very difficult for that person to interpret, to understand. Okay, so we have RMSE, which has the same unit as the dependent variable. Okay, now even RMSE has a disadvantage. Okay, let's see what is that. RMSE also has a disadvantage. Now let's say I tell you that my RMSE is 10. The RMSE of a model is 10. Okay, and somebody else tells me that the RMSE of another model is 20. Okay, now which model is good? Which model is better here out of the two? Okay, actually you cannot say which model is better. Now let's say the actual value here, the actual value was 10. Okay, so RMSE represents on an average how much error are you making. Okay, that is what RMSE represents. On an average, how much error are you making? So this means that on an average you are making an error of 10. Okay, and this means on an average you are getting a error of 20. Okay, but getting an error of 10, still it is not interpretable. It is still not interpretable because you don't know what is your actual value, right? This is like a absolute error. Both these numbers are like absolute errors. So you know that your error is 10, but 10 out of what? Let's say my actual value was 100 and I made an error of 10. Okay, this is case 1. And my actual value was 1000 and I made an error of 10. This is case 2. So which case is better? Okay, of course case 2 is better, right? Of course case 2 is better, because here out of 100 you are making an error of 10, but here out of 1000 you are making an error of 10. Okay, but if I just give you the value of error, it becomes very difficult for you to judge because you don't know what the actual value is. What if the actual value was also 10 and your error was also 10? That means your error is 100%, right guys? The error was 10 and the actual value was 10 and your error was also 10, so that means you predicted 20, right? Are you getting the point? Because this is an absolute value, it is very difficult to judge the error based on this. It will tell you which model is better. We know that this model is better than this, but we still fail to understand that how good is this model, because it gives you an absolute value. It gives you an absolute value, but we often compare how much error are we making with respect to the actual value. So that is why we have another error term which is known as mean absolute percentage error. Okay, this is known as mean absolute percentage error. Okay, so did you understand the need for this error? Why do we need this error? Because this is still not very interpretable, because it gives you an absolute value. So for example, this case, you got an error of RMSE of 10, but with respect to what, it doesn't tell you. But if you take a percentage, then this will be 10% and this will be 1%, right guys? 1010, it is 1%. So if you calculate as a percentage, you can easily know which one is better. So of course this is better because it is 1%. Okay, and percentage means you can scale it to any number. So even if it was 10,000, 1% error means it would be 100. Okay, so you can easily scale it up. So the formula for MAPE is, so first the error, again going from last, going from the right hand side. So first is the error, which is actual minus predicted. Then you take the percentage, so you divide it by the actual. Okay, you take the absolute value of it, and then you take the mean of it. Sum everything and take the mean of it. Okay, this is your formula for mean absolute percentage error. Is this clear, guys? It's a simple formula, nothing difficult, just a formula which you will have to remember. And it's easy to remember. Just remember MAPE, mean absolute percentage error. Mean absolute percentage error. Is it clear, guys? So whenever we work on any project in the industry, we actually report these values to the customer, to the client. Okay, you will report your R square, you will report your sum of squared error, you will report your RMSE. So generally we just report R square and we report MAPE. Okay, and sometimes RMSE also. This we don't report because this is not at all interpretable. But the other three quantities we generally report to the client, and then the client tells us whether he is happy with that or not, or he wants us to improve better. Okay, if let's say we report some R square and if he is not happy with the R square, the client will tell us that I want a better R square, I want a even better R square. So then we will go back and try to change something in our model and try to get a better R square. Okay, similarly if we give a MAPE and the client is not happy with that so let's say our model is making 15% error, but the client is not happy with 15%, so he will tell us that no, 15% is too much, I cannot go beyond 10% error. Then we will come back and change our model and try to reduce the MAPE to 10% or less than 10%. So that is how it works. Okay, so now let us find the MAPE value for both the models that we built. So this is your R square. Okay, I did not find the RMSE for the first model. Let me find the RMSE for the first model. Okay, I found it here. It's here. Okay, so I'll find the value of MAPE now. Okay, so MAPE is nothing but I can take linreg1. First thing is I have to calculate the error. Okay, so residuals. So this residuals is nothing but actual minus predicted. I will divide that by the actual values. My actual values is in empty cars, dollar miles per gallon. These are my actual values. Okay, so I have divided my actual minus predicted by my actual. I will take the absolute value of it by using the function abs. Okay, then I will add all of this together. And finally divide everything by the number of rows that I have, divided by n row empty cars. Okay, this will give my, oops, I missed a bracket. Okay, no, oops. So okay, so playing with brackets is very difficult. Okay, so be careful when you're doing this, it's very confusing sometimes. So make sure you close the brackets that you open. So I've created a sum of, so first is this residuals, then I'm taking the absolute value residuals divided by this. Okay, so absolute value of this. Okay, this is not required, I think. Yeah, so 12% is my error, 12.6%. Okay, you can multiply this by 100 if you want it in percentage, or you can leave it like this. So 12% is the error of this model, the first model that we built. 12% is the error. So similarly I can calculate the error for the second model. I'll just copy paste the same thing. I'll copy paste this, and I will change linreg1 to linreg2. Okay. Now if I run this, so 22% is the percentage error for the second model. So all the parameters are telling me the same thing, basically, that my first model is better than my second model. Okay guys, so this is how you create your models in our linear regression models. This is how you create. Okay. Yes guys, any doubts so far, tell me. These things will be same for all models. Okay, for all regression models, the evaluation parameters will be the same. We will use the same sum of squared error, RMSE, and MAPE to evaluate all regression models, not only linear regression model, but all regression models. Yes, Abhilash, that is correct. R square and MAPE is sufficient to predict better model. Okay, so we generally, most commonly, we use R square and MAPE, but sometimes we add RMSE also because it's not difficult to calculate. So if you have worked so hard on creating a model, why would you hide any values from the customer? You will show everything that you have. No, Lalit, I will come to that. So right now what we are doing is a univariate linear model where we are taking only one independent variable. We will do a multivariate linear model also where you will have 3, 4, or 20 independent variables simultaneously. So simultaneously you will have 20 independent variables in the same model. That is where the complexity is increased. Okay. So just take a moment and absorb this, then we'll move ahead. No, Lalitya, but these are different models, right? And you, in all of these, in both these models, you have one independent variable, right? See, dependent variable will always be one. Okay, let's be very clear with that. Dependent variable will always be one because that is what your business defines. You cannot change that. Okay, but independent variable, you can have many independent variables. Okay, you can have many independent variables, but in one model you have only one, right? So in linear regression 2 you have qsec as your independent variable. In linear regression 1 you have weight as your independent variable, but each model has only one independent variable. So this is a univariate model. This also is a univariate model. Okay, when you have multiple independent variables in the same model, then it is known as multivariate. Yes, Mrityunjay. So you will basically submit your best model to the client. So you will do all possible iterations at your side, and you will submit your best model to the client, and then finally the client will decide, or the stakeholder will decide. It can be your own company or somebody else. He or she will decide whether they are okay with that model or not. So it can be your some other department of within your company itself, right? So let's say marketing department of your company. So analytics will be a core skill organization within a company. Okay. So you will have a core central team of data scientists which will serve all the other business units. If you are a product based company, if you are not a services company, then you will have a core team which will provide services to other business units. It can be your sales department, your HR department, your marketing department, or whatever. Okay, in HR also a lot of analytics is done. So they will take the final decision. Yes, bigger, not bigger the data frame, more the columns, more difficult it is. Okay, because more columns means we will see that in details. Rows is good for us because more rows means more data point we will get. So more data points means it becomes better, it becomes easier for the model. But more columns is not good, especially if the columns are not adding value to your dependent variable. If your columns are not correlated to your dependent variable, it is not good. But you always have the option to omit them. You can always omit the not non-important ones, right? So no big deal. Okay. So now let us come to multivariate linear models. Okay. So we are done with univariate models. They are very simple, easy to understand. So you have understood all the concepts. Now I will come to multivariate linear models. Okay. So we will start with multivariate linear regression models now. So what difference do multivariates have? The only difference is that they have many independent variables. Okay. So if you have many independent variables, your equation will look something like this. So it will look like beta naught plus beta 1 x1 plus beta 2 x2, for example. So I have included here, I have included two independent variables. Okay. So what is this equation? What does this equation represent? Can somebody tell me? High school mathematics, guys. This is high school mathematics. Yes, that is true. No, this is not a polynomial. This is the equation of a plane. Remember, in class 10 you would have studied what is the equation of a plane. The equation of a plane is ax plus by. Okay, ax plus by is equal to 0. This is the equation of a plane, if you remember. So this is class 10. So when you have two variables, so now your data is in two dimensions. Okay, so you might have something like this. This is your x1, this is your x2, and this is your y. So you can no longer draw a line because a line can only take one dimension, right? A line is a one dimensional figure. So now you will have to draw a plane. Okay, you'll have to draw a plane now. So this is the equation of a plane. So instead of a line, now you will draw a plane to predict your dependent variable. Clear, guys? Okay. So that means your output will look something like this. Okay. Your output will look something like this. It will be a plane like this. Okay. So don't worry about what is written on the slides, parametric, non-parametric. We'll cover that later. But right now, just focus on this. Okay. This figure. Just focus on this figure. This is your y. This is your income. So this, they have explained this with respect to one example. This is your income, and your income is now depending on two things: years of education and your seniority. Okay. So it is depending on two things now. If previously it was depending on only years of education, so you were directly drawing a line. But now it depends on two things. So a line will not work. You'll have to draw a plane like this. So this plane will be what you will be looking for now. So y is equal to beta naught. You will have the intercept plus beta 1 x1 plus beta 2 x2. So this yellow figure that you see is the equation of this plane. Okay. Clear, getting, guys? So that plane will help you find out the value of y now. So both these variables will influence your y, both seniority and years of education, and they will have a different coefficient now. Okay. So now this is considering two independent variables, right? This is considering two independent variables. Now I can extend it beyond two also. I can also write something like this: beta naught plus beta 1 x1 plus beta 2 x2 plus, I can go on and on till beta n xn, where n can be any number. Okay. I can include as many variables as I want. Now we don't have a name to this figure, so we can only visualize till two dimension. So that is why we only have till plane we have. If you include three, what will you call that? We don't have a name for that. Okay. But that will be some complex structure, but it will be linear. It will still be linear, but it will be some complex structure. It will be one dimension more than a plane. Okay, but it will be linear. So we cannot visualize that, but till two dimensions we can visualize. Okay. So somebody gave the answer polynomial for this, right? So polynomial equation, I'll show you how it looks like. A polynomial equation looks like this. This is a polynomial equation. Okay. Not this. This is not a polynomial equation. You can say that this is also a polynomial equation because you can add something here, right? So 0 into x4 plus 0 into x cube. You can add this here and say that this is also polynomial. Okay. But ideally these terms are 0. So it is, so polynomial means everything comes under polynomial only. Even a straight line is a polynomial equation basically, because these terms are 0. But practically if you see, it is not polynomial. Okay. It is linear. This is also linear, whereas this is non-linear. If you draw this, it will be a curve. Okay. But these will be straight lines or planes. Okay. So now this is all about multivariate linear regression. In R, it is very easy to execute this. So for example, what were we using till now? We were using miles per gallon tilde symbol, and we were giving weight, right? Now if you want to include more variables, you just write plus. Let's say I want to include horsepower, I write plus horsepower. You want to include something else, let's say the number of gears, you write gears. And whatever you want, you just write it by giving a plus sign. And finally you write your data is equal to empty cars. Done. As simple as that. You use lm, same lm function, you give some name here, same again as before, linear regression 3 model, and you do this same process. If you have to study the output for this, you write summary, and whatever name you give that name here, and you will get a similar output. Clear guys? Do you understand how do you do a multivariate analysis? And all the other parameters will remain same. You will have the same r square, you will have the same sum of squared error, you will have the same way of calculating RMSE, same way of calculating MAPE. Everything remains same. Only difference is instead of one, you are adding multiple now. Clear? Easy? Guys, are you there? Okay. Please respond when I ask something, okay? Because that is how I understand whether you guys are following or not. So if you don't respond, I will be totally confused whether I should proceed ahead or I should go slow. That is the feedback you give, right? The chat box. I cannot see your faces. It's not a literal classroom. Yes, Mrityunjay. So that is where the challenge lies. If you select a good variable and a bad variable, you may not get a very good model. So ideally, you should select all good variables. So that is where the challenge lies in machine learning. How do you select the good variables? Okay, so that is the challenge which we will see now. So let's execute a multivariate in R now. So I will call it linreg3. Okay, I'll call it number 3, linear model. My dependent variable is same, miles per gallon. And then I will take weight. I will take, let's say I will take horsepower, and let's say I will take gears, number of gears I'm taking, okay? And I will give data is equal to empty cars, and I will run this. Okay, so the model is done. I will just write a summary, and I will see the summary output of linear regression 3 now. So I run this, I get something. Okay, so let's study the output now. Okay, so the first thing is still the same, no difference here. Same formula it is giving me, same residuals it is giving me. Now come to coefficients. Now you see I have coefficients. I have this beta naught. This is my beta naught, okay, 32. My beta 1 is my beta corresponding to weight is this minus 3.19. My beta corresponding to horsepower is this, and my beta corresponding to gear is this. Okay, so if I have to write down the equation now, how will it look like? My equation will look like this now. Miles per gallon is equal to 32 minus 3.19 into weight minus 0.03 into horsepower plus 1.01 into gear. Is it clear guys? Do you understand why the equation will look like this now? Okay, this is simple, right? So this what you saw was our linear regression line. Then it's not a line, but we usually call it a line because we don't know the name for it. So that was the linear regression line that you got. or linear regression model that you got after taking these three variables into account. Okay, now let us see the other things. So standard error, you already know what it is. T value, you already know. Let us come to this p value. Now we have to identify which variable out of all that we have included which is important. Okay, so we can do that using p value. So you can see the stars also. The important variables will have stars associated. So the first one, intercept, is important. Okay, weight is important because the p value is 0 for that, 0.0007. Horsepower is also important because it is 0. You can check the stars also. But what about gear? So do you think gear is important? Yes, guys, do you think gear is important? Because it has a higher p value. So in gear, what are you getting? The p value is becoming greater than 5%. So let's come back to the hypothesis test here. So the hypothesis test with respect to gear. So for each variable, you will have a hypothesis test going. Okay, guys. For this, you will have a hypothesis test. For this, you will have another hypothesis test. For this, you will have another hypothesis test going on. So for gear, the null hypothesis will be that the beta corresponding to gear is 0. Okay, and the alternative will be that the beta corresponding to gear is not 0. Then you find your p value. Again, I will not go into the definition again. You find the p value, and the p value that we get is this 0.24. We are getting 0.24 or 24% as the p value. Now 24% is greater than 5%, right? So p high, null fly. So that means we fail to reject null hypothesis. We fail to reject null hypothesis. That means this is correct. So beta for gear is equal to 0. So that means we will not consider what beta we are getting here. We will consider beta as 0. So that means if I write the equation again, miles per gallon is equal to 32 minus 3.19 into weight minus 0.03 into horsepower plus 0 into gear. So it will be like this. I cannot take this value because I cannot reject my null hypothesis. Or if you don't want to go into all that details, just select the variable which has at least one star and ignore the rest. Okay, but now you know the reason behind it. So in interview you can be asked the reason. Why do you consider only the stars? Why not the other stars? You know the entire statistical reason for that. Okay, and if you are able to explain that to the interviewer, that will be a pretty impressive interview. Not many people know that. Okay, so this is your final equation now. This is irrelevant because this is anyway 0. So whatever gear you add, it will not add any value to your miles per gallon. Okay, so this is your final equation after multivariate linear regression. Clear, guys? Okay, so till here we are done. Now let us see this value. Same, this line you can ignore this line. Now same, we are getting r square as 0.83. See, the r square also improved. Previously I think we were getting around 0.7 something as maximum. Now we are getting 0.83. So the r square became better now. Okay, the r square became better. We will see what this adjusted r square means. Okay, we will see what this means maybe later, maybe next day. But right now just focus on this multiple r square. What is this multiple r square? So everything clear till now, guys? Even if we keep the values, does it make a difference? Which value, Abhilash, which value are you talking about? No, it doesn't matter because it is 0, right? So ideally you should exclude it. Okay, so let's see what happens. So ideally you should build another model without considering gear, because sometimes it will decrease your value. Okay, so we will discuss that now. Should you include gear or should you not include gear? We will discuss that now. Can you repeat your question, Dibakar? I did not understand. Which part are you confused with? Okay. Which part here? This one? The stars? You mean this one? Okay. Yeah, this just means that if your p value is in this region, in this range, if your p value is between 0 and 0.001, you will get 3 stars. That is why you have 3 stars here, because this value is less than 0.001. It is 1.64 into 10 to the power minus 7. Okay, so 0.0000 something. So it is between this range, right? So you have 3 stars here. If it is between these two range, it will have 2 stars. If it is between these two range, it will have 1 star. Now our p value for gear is 0.24. 0.24 lies in this range between zero point 0.1 and 1. So that is why you don't have anything. You don't have anything here because it lies in this range. Now is it clear? So even if you don't understand hypothesis testing, you can just look at the stars and you can select which variable is important. So this is R's way of telling you. Because initially only statisticians used to understand the entire hypothesis test and everything. But now slowly as data science became more popular and more people started learning data science, things became a little more popular and people started diving deeper. Then even non-statisticians, they started understanding that what is the reason behind these stars. So we have all the hypothesis test and everything. Okay. Okay, now let's study R square in details. Okay, so let's see how is R square calculated. Okay, so there is a formula for R square. Okay, the formula is 1 minus SSE. You already know what SSE is, divided by TSS. TSS is, okay, or I can say TSS is SSE from a baseline model. Now what is a baseline model, guys? Anybody remembers? We discussed it, I think, day before yesterday or yesterday. What is a baseline model? Yes, no independent variable. And what does it predict? If there is no independent variable, what does it predict? How will it predict if there is no independent variable? Straight line. No, even linear regression is a straight line, right, Dibakar? Even linear regression is a straight line. Parallel to x-axis, but at which point? There can be infinite lines parallel to x-axis. Which line will I select? Yeah, what is that constant y value? Yes, that is the average. Okay, so the baseline model always predicts the average. So remember the example that I gave you, that there are three guys who work in a team. The salary of one is 10, the salary of other is 20. You don't know the salary of the third one. If you have to guess his salary, you will guess the average, right? That is the best guess you can make. Okay, that is why I had drawn the line at 15, because no matter what independent variable you take, the baseline will not even consider the independent variable. It will just predict flat 15 lakhs, the average. Okay, so this is your baseline model. So sum of squared error, you already know how do we calculate that. So sum of squared error, you know how to calculate. Can we calculate total sum of squared error? So total sum of squared error is nothing but sum of squared error, but with respect to a baseline model. So can I write it as like this: ya minus y predicted whole square summation of this, where y predicted is your y actual average of that. Can I write it this way? Is it correct? Okay. So this is what we will do. So let us calculate r square manually. So this is the formula for r square, and you have to remember this. This is asked in interviews a lot. So you have to remember it, not very difficult. 1 minus SSC by TSS. Let us calculate r square by using this formula. Okay. So let me go to R. So I'll not calculate for all the previous models. I'll just calculate for this model. You can calculate for this model also. The same formula will apply. Okay. So I'll only calculate for this third model. So sum of squared error, let me calculate. I can calculate sum of squared error by taking lin reg 3 dollar residuals whole square and sum of this. Okay. So my sum of squared error is this 185. Similarly, I can calculate my TSS also. My TSS, I can just copy this formula. No, I cannot copy that formula. The formula will be different. So my actual value, which is empty cars dollar miles per gallon, minus my average of empty cars dollar miles per gallon. Okay. So actual value minus the average value, and then I have to square this and then take the sum. Did you guys understand the formula? This will be my TSS. Okay. Then to find r square, what will I do? I will do 1 minus SSE divided by TSS. Okay. Now I can print my r square. It is 83%, which is what I got by r also. See, I'm getting the same answer. So you can calculate r square manually also. You don't have to depend on r's ability all the time. So sometimes they will ask you the entire formula and ask you to calculate r square. In interviews, they'll give you a system and they'll ask you to calculate r square. Okay, is this clear, guys? How do you calculate r square? Okay. Now just one more additional thing we have to see is, so you must have seen here, right? We were trying to avoid this till now. We have seen what is multiple r square is nothing but the r square that we are talking about. Okay, that is known as multiple r square. Now what is this adjusted r square? Let's see what is this. So this is the only thing that is remaining. Let us finish this off. Okay. So adjusted r square. So r square has a disadvantage. Okay. R square has a disadvantage. Okay. The disadvantage is that r square goes on increasing even if you add some crab variable. So your r square will increase even if you add some insignificant variable. R square goes on increasing. Okay, but that doesn't mean your model's accuracy has improved. Okay, that doesn't mean that your model's accuracy has improved, because that is a property of r square, that it goes on increasing. So that is why it is very difficult to say whether your model is good or not just looking at r square. It is very difficult to judge. So to avoid that, or to compensate for that, we have an additional parameter called adjusted r square. Okay, so adjusted r square, as the name suggests, it is very similar to r square, but it pays a penalty. It pays a penalty if some insignificant variable is included in your model. If some insignificant variable is included in your model. So if you include any variable which is not adding any value to your model, your adjusted r square will not increase, but it will decrease. Okay, it will start decreasing. This will anyway increase, but if it is not significant variable, this will start decreasing if you add such variables to your model. Okay, so adjusted r square, it penalizes the value of r square if you add insignificant variables to your model. So that means adjusted r square is the true indicator of a good model. Is a true indicator. This also takes the same range, 0 to 1. Okay, in all other aspects it is similar to r square, but except this difference. So this is the true indicator of a good model, adjusted r square. So we should always look at adjusted r square and not r square. R square you can ignore. Okay, and there is a formula for adjusted r square also. It's a big formula, you can google and know. I don't remember that, and nobody is supposed to remember. It's a big formula which involves degrees of freedom and so many other things. Okay, but this is what you should know. Why do we use adjusted r square? Is it clear, guys? So this is the last topic for today. We are not going into anything new. Yeah, so this week will be very crucial for you guys, because next week will be again new topics and a lot of new topics. From now onwards, all the weeks will be like that. In fact, that is why I was telling you guys that from day one you should give full effort. You cannot keep things to do next week, because next week will involve many more new things. So your backlogs will keep piling, and at some point it will become too difficult to manage, and you will just quit studying. That's what happens. Okay, if 20 people start studying data science, almost 8 of them will quit halfway. 8 of them will quit halfway, and only 12 of them will continue till the end of the class. Okay, out of that 12, another 3 will quit towards the end of the class. They will quit towards the end of the class, and only around 9 or 10 will remain. Out of that 9 and 10, again another 2 or 3 more will quit. So they will have studied everything, but they will not revise it. After the course ends, they will not revise it well, and they will forget everything and they will quit. So finally you will have 5 or 6 people remaining who have revised everything, and who will be looking for jobs. Okay, and out, so five will be looking for jobs, but again only 2 or 3 of them will basically be able to sell themselves. Okay, so we will discuss about that. That's a different topic. So just knowing data science is not enough. You should know how to search for jobs, where to search for jobs. Okay, so that also is very important. So 1 or 2 of the students out of the total 5 or 6 will not be able to do that properly, will not be able to sell themselves properly. So finally you will have 3 or 4 students getting jobs. But so if you see as a proportion of total, it is only 4 students out of 20 who started. So if you see the success ratio, it is not that great. But if you see how many got success out of the people who completed the entire course and who studied, you will see it's pretty big actually. So out of 6 people who completed everything, 4 of them got jobs, so almost 80%, which is not bad. So you have to be motivated, really motivated to go till the end of this course, and follow till the end of this course. So that is why you have to give consistent effort. You cannot say that last 2 3 weeks I will study. It will not work. You will lose track. Okay. So Mitunjay is asking, can we not find R square of individual independent variables, and then based on the highest ones we can choose them for our multivariate model? Yes, you can do that, Mitunjay. So you don't have to find R square for individual independent variables. You can just find R instead of R square. Because for R square you have to run the model. But to find R you can directly do it without running the model. That is why R is so important. R helps us to identify which variable alone will be important to identify or to predict your miles per gallon. That is why we included small r. Okay, so if I take you back to the code of small r, see, r square is dependent on these values. So you don't have to find r square to say which variable alone is important. So that means, so if from here what can you say? This is not a combination of variables, Lalitya. This is each variable alone. Okay, this is each variable alone. How important is this? Now r square can give you together how important are the variables. Adjusted r square. Okay, adjusted r square will give you that all these variables together, how good are they. Right now these are all alone, they are telling you. So alone, if you see, displacement or weight is the most important if you see alone. Okay, so what we usually do is we identify which is the best variable from the correlation matrix. So this is our correlation matrix. We will identify the most important variables. So we have weight here, we have horsepower, displacement, and diameter ratio. So we should ideally include these 3 in our model. Okay, so let's do another model where we'll take these 3 variables, these 4 variables. Okay, so linreg 5 lm, miles per gallon, tilde symbol. I will write DISP plus horsepower plus DRAT plus weight. Okay, data is equal to data frame. Data is equal to MT cars. I run this and then I run the summary function linreg 5. This is 5 only, right? Not 4. Okay, it should be 4. Okay, I run this. So see, now you can see, right? See, r square increased, but my adjusted r square has decreased. It has become less now. So that means the variable that I added, diameter ratio, is not helping my model. See, the r square is, the p value is 19%. So that means, and even this displacement also is very high. So ideally I should not include displacement and diameter ratio. I should just include horsepower and weight. Okay, so let me remove them. So let me remove this, and let me remove this. This is my linear regression 4. So I'm getting 81%. 81% adjusted r square, which is quite good. So here I was getting 81% 36. See, it increased now. 81.48. Previously I was getting 81.36. Okay, but if you see r square, the r square for this was higher, because even if you add insignificant variables, so these two were insignificant variables for us. So even adding insignificant variables, it increased our multiple r square, but adjusted r square had decreased. So this is a better model than the previous one. So we will finally take this model. Clear, guys? So there are a few more things remains in linear regression. We will cover it in the next class. Okay. So we will have to spend another 1 hour in linear regression actually. There are a few things which remains in linear regression. We will cover that in the next class. But whatever we discussed today, are those clear, guys? Of course, you will have the recordings and you will have 5 days time to work on this. So you can watch the recordings maybe once or twice. I'll send some materials as well for you to read, or some homework as well I will send. So do those homework and try to finish the homework before the class. Okay. So I might send you the homework by Wednesday. Okay. But till Wednesday, make sure you understand all the concepts. So don't wait to understand the concepts when you get the homework. So Wednesday, when you get the homework, you should be thorough with the concept so that you will quickly do the homework within 2-3 days. So by Saturday, you should be done with the homework. So finish all the tasks weekly. Don't keep anything pending for the next week. Otherwise, someday it will become too much to handle. Okay. If you are taking this course seriously, trust me. And trust me, this course, if you take it very seriously, if you forget about anything else for the next 1 or 2 months, trust me, by end of the course or after 1 month of completion of this course, you can easily crack a job. But if you are taking the course seriously, at no place you will get a course such detailed. I myself take courses in training institutes in Bangalore. The syllabus that they have is horrible actually. That they will just give a high level view. They will not go into details. So that high level view is not enough to crack a job. So it takes people 8 months, 10 months to be job ready in the courses of training institutes. But for this course, I am not bragging. Okay, I'm not beating my trumpet, but no course will go in such details. This course alone is enough to get you a job. And some of the students that I have had, they were good enough, they worked very hard, and just 15 days, 20 days after the course ended, they cracked a job and they are now working as data scientists. And they had experiences. They were not even they already had around 6 or 7 years experience in a totally different field, but they just faked their experience and they cracked interviews. They showed some dummy projects. So the projects which I included in the course, they showed those projects as their actual projects in their offices, and that helped them crack jobs. Take this course seriously. Okay, just 2 months focus on this course. And I'm not asking a lot. I'm just asking around 10 hours every week, outside the class hours, which is not a lot. 10 hours every week you can give. So 1 hour daily, 1 to 2 hour daily you can give. So try to find half hour from that 2 hour in your office hours. Doubts, guys, from today's class? Okay, then we can go for a revision. So are you guys okay with a class on maybe Wednesday or Thursday, just for 1 hour at late, maybe 10 o'clock in the night, 10 to 11? Because I want to finish up this linear regression thing before next week. Next week I want to start with something new. Otherwise, this will eat up our time. We are going too slow, guys. If we go this way, it will take us 100 hours to complete the topics that I have planned. Okay, what time do you reach home, Niranjan? Around 11. Oh my god. So you work in second shift? Okay, then that is a problem. But maybe one day you can come early, right? If we fix the timings, one day you can manage, right? Nope. Okay, then let's see. We will have. Okay, then it's okay. We will do it on weekend only. Okay. So let us start the revision now. Yeah, we can do that. So we can have 4 hours on Saturday and Sunday. So 8 hours. But actually, I don't want to drag the classes to 4 hours because after some point of time, you would get too tired to understand something new. So the effectiveness of the class reduces. So I don't want to make it 4 hours on a single day. If we distribute in small hours but more days, that way it is more effective. I think I messed up with the class notes. I added both and I saved it on the same. Model evaluation. No, I think I'm good. Okay, guys, so let's start with revision. We covered a lot today. Not a lot, I would say, but too many important things we covered. So let's revise everything. Yes, can you help me, guys? What else did we cover? So linear regression, we saw that the if we include first we did a univariate linear regression. Okay, a univariate where you have just one independent variable. Okay, so this is pretty simple. We saw we saw that to evaluate this model, how good is the model, we have some parameters. One of them is r square. R square is the accuracy parameter. Okay, R square is the accuracy parameter. Higher the better. Max value it can take is 1. Okay, so this is your accuracy. Similar to accuracy, we have some other parameters also which helps us identify how good is a model. So the others are the error parameters. Okay, the other are error parameters. So lower the value, the better it is. So the first is sum of squared error. Sum of squared error is nothing but actual minus predicted whole square, and then you add everything. Okay, sum of this entire thing. So obviously lower the better because this is error. Okay, this suffers from a disadvantage is that not interpretable. This is not interpretable because of the units. Next we saw is root mean squared error, which is, so as the name suggests, error square, mean, root. Take the mean and then take the root. This is your root mean squared error. This is good. This is interpretable. This also lower the better. This is interpretable, but one disadvantage it has is it is absolute. It is absolute value, so it is very difficult to compare. Okay, so for that you have another one, which is MAPE, mean absolute percentage error. The formula is actual minus predicted divided by actual, error percentage, absolute I've taken, and then the mean. So you add everything and you take the mean. Okay, this is your mean absolute percentage error. Obviously lower the value the better it is. Now this is very interpretable and this is relative. Okay, so this is the best one. Then in R square we saw the formula for R square. What was the formula? We saw that the formula, okay, let me write it here. So R square, also known as multiple R square, the formula for this was 1 minus SSE by SST. This is SST or TSS, it means the same. Okay, both means the same. Total sum of squares or sum of squares total. You will see both these terms in books. Okay, sum of squared error you already know. SST is from a baseline model. SST is from a baseline model. What is a baseline model? Always predicts the average. Always predicts the average of dependent variable. Okay, so if I have to calculate SST, it will look like y actual minus y actual's average. Okay, this is your average and you take the sum of this, square this and take the sum. This is your total sum of squares, TSS or SST. So this is your multiple R square. Now multiple R square has a disadvantage. Multiple R square has a disadvantage. The disadvantage is that it increases even if you add junk variables. Okay, even if you add variables which are actually not helping your model, even if you add variables which are not helping your model, your R square will still increase, your multiple R square, which is not good. So it is very difficult to judge how good a model is just based on R square. So R square is not used. We have another parameter similar to R square, which is known as adjusted R square. Okay, so adjusted R square is the true measure of accuracy. Okay, this what it does is it penalizes the R square. It penalizes R square if junk variables are added. If junk variables are added to your model. Okay, so that is why it is the true measure of accuracy, because if your adjusted R square is good, that means the model has all the important variables. Okay, then what else did we see? We saw the hypothesis test in the output of a linear regression model. So in the hypothesis test we saw that the null hypothesis is that, so let's say you build a model y is equal to beta naught plus beta 1 x. Okay, so your null hypothesis is that beta 1 is equal to 0. That means the variable x is not helping your model. Okay, it is a junk variable, it is not useful to predict y. That is your null hypothesis. Your alternative hypothesis is that beta 1 is not equal to 0. So starting with this two assumptions, you calculate your p-value using a t-test. Okay, and whatever p-value you get, based on that you take a decision. Okay, if your p-value is greater than 5%, your null will be accepted. If your p-value is less than 5%, you reject your null. Reject your null. That means if you reject your null, that means this is not correct. So beta 1 is not equal to 0. Then what is the value of beta 1? The value that the output is giving you. that is the value of your dependent variable. So this beta 1, whatever beta 1 you get from the model, you take it. But if your p value is greater than 5%, then you fail to reject your null hypothesis. Okay, that means beta 1 is 0, so you cannot include this term. Your equation will just be y is equal to beta naught. Okay, so the same thing, the same understanding you can also directly do without going into all details by looking at the stars in your p value. So 3 stars means it is very important, 2 stars means it is important, single star means somewhat important, and beyond that it is not important. So we look for at least 1 star in our p values, and you will get these p values corresponding to all the variables that you have included. So until now we have discussed about, so this revision was for univariate analysis. We also saw what is multivariate multivariate linear regression, where you include more than one variables. So this is how you give dependent variable tilde, independent variable 1, independent variable 2, and independent variable n. Okay, data is equal to the data frame. This is how you define same way. So now you'll have many different values now. So you will have your coefficients. So you will have one coefficient for 1, for 2, for 3, and then for n. And from each of these, each will have its own p values. Okay, p1, p2, p3, p4. Now looking at all these p values, you will take a decision that which variable is important and which is not. Looking at the p values, you will take that decision. So if you get, let's say, 2 stars here and 1 star here and no stars at the other place, that means only these two are important. Okay, so you should create another model. You should remove them from your model. That means having them in your model will not make sense. So you should create another model with only these values, with only the values which are actually helping your model, and you should exclude the other two. That will be your final model. Okay, and guys, in a univariate analysis, in a univariate linear regression, your r square and multiple r square and adjusted r square, they both are almost the same, because you have only one variable, right? So one variable means adjusted r square has no significance. It is, your accuracy can directly be taken from multiple r square if you have only one variable, because only if you have more than one variable the penalization starts. Okay, if you have just one variable, there is no need to penalize. You have just one variable. Okay, r square and adjusted r square will be almost same. Okay, anything else that we covered today? Guys, anything else did we cover today? Yeah, we covered correlation. So apart from r square, we also saw small r, the correlation coefficient. So this is a quantity which gives you the linear relationship between any two variables. Okay, it gives you the linear relationship between any two continuous variables. The formula for that is xi minus x bar divided by sigma x, yi minus y bar divided by sigma y, and you take the mean of this quantity, mean of both of them. Okay, this into this, you take the average of this, and you get your small r. This is a value between -1 to +1. And your capital R square, the coefficient of determination, is nothing but the small r between your actual value and your predicted value, whole square. Okay, we have seen this formula also. But don't try to confuse between small r and capital R. Okay, S- Capital R is for linear regression. Small r is from mathematics. Okay, that is general mathematics. You are directly proportional or inversely proportional. Okay, it is that mathematics. But capital R is linear regression. It is modeling. It is machine learning. Okay, yes, we will discuss that. Just give me a moment. Let me update this. I forget what did I cover. Anything else apart from this? Okay, I think this is all right. Sure, Disha. Okay, so let's quickly discuss the interview questions that can be asked from today's class, and then we will wrap up. Okay. So, guys, a lot of things can be asked from today's class. Today was your first class of machine learning. Okay. So you can be asked many different things. First is subjective questions can be asked, like define linear regression. What do you do in linear regression? Tell me everything you know about linear regression. So those kind of questions can be asked. Okay. So there you will have to explain everything. Okay. Then what you can be asked is simple questions like what is R square? Tell me what is R square, or they will ask you what is coefficient of determination. That can be one question. So you'll have to say that it is a parameter which is used to evaluate a linear regression model. and then you can give its equation also, that r square is equal to 1 minus ssc by sst. Okay, then they will ask you what is ssc, what is sst. You tell them all those things. Okay, sst is coming from a baseline model and so on, you will tell those. Then they might ask you what is the difference between r square and adjusted r square. What is the difference, why do you use adjusted r square? Then you will say that r square is what you have just talked about. And so r square, the disadvantage of r square is that it always increases. Even if we add junk variables to our model, it increases. Okay, but adjusted r square, what it does, it penalizes r square if it adds any junk variable. So if you include junk variables to your model, adjusted r square penalizes your r square for that. So that is why adjusted r square is the true measure of accuracy, not multiple r square. It is adjusted r square which is the real test of a model, real parameter which you should look at basically. Okay, so that is about the difference there. Then they might ask you, explain me hypothesis testing. What hypothesis testing goes on in linear regression? That can be a question, a very important question. Okay, so on the stat side, what hypothesis test is covered in linear regression? So you will say that, so in a linear regression, the null hypothesis is that the variable that we are considering is not important. So when you say the variable is not important, the coefficient of the variable becomes 0. Okay, so beta I, whatever I is, beta 1 is equal to 0 is your null hypothesis, and your alternative hypothesis is that beta 1 is not equal to 0. Okay, then you do a t-test there, and using a t-test you find the p-value, the observed significance level, and the p-value, depending on whether it is greater than 5% or not, you either reject or you fail to reject your null hypothesis. Okay, if your p, so ideally you look for p-values less than 5% because you want to reject your null hypothesis. Only if you reject your null hypothesis you will find important variables. Okay, so you look for variables which have less than 5% p-value, so that you can reject the null hypothesis, which is that the variable is not important. So if you reject that hypothesis, the variable becomes important. So you have found an important variable which you can include in your model. So that is the null hypothesis or hypothesis test in a linear regression model. Then other question which can be asked is, what are the other evaluation parameters of a linear regression model? So you will say that the other evaluation parameters are sum of squared error, but sum of squared error has a disadvantage that it has squared units, so it is not very interpretable, it doesn't make sense. So you have root mean squared error. Root mean squared error tells you it has the same unit as your dependent variable, and it tells you on an average how much error are you making on an average. Okay, and then that also has a disadvantage that it is absolute, it is not relative. So when you say that you have a RMSE of 10, it is very difficult to say that 10 with respect to what, with respect to 100 or with respect to 1000. If it is with respect to 1000 you are okay, but if it is with respect to 100 it's not a very good model, 10% error you are having. So that indication is lost if you say the RMSE. So for that we have mean absolute percentage error, which gives you the error as a percentage. Then you tell him the formula for each one of them. Okay, so that is what can be asked. Then another question that can be asked is, what is correlation, and why is correlation important? So you cannot go and run model every time you want to identify an important variable. Okay, so for that you can quickly run correlation. So correlation helps you identify important variables without running a linear regression model. So it's a small test kind of a thing. Okay, it's like a qualifier round, you can say. Okay, it's like a qualifier round. Only variables which have high correlation should be taken ahead to your linear regression model. Okay, so let's say you have above 0.60 correlation with your dependent variable. Okay, that is important. So your correlation small r should be high with respect to your dependent variable. You can keep changing these variables. You can take first independent variable, second, third, nth. Okay, whichever gives high correlation with your dependent variable. By high I mean greater than 60%. Okay, absolute. Whichever gives greater than 60%, you select those and take them to your linear regression model. Okay, that is what is done. So that is pretty much it, guys. So are things clear, guys? Did you understand? This was your first machine learning model. So next week we will need another maybe 1 or 2 hour to, so a few more things remains in linear regression. So we will cover those in the next class. And